When it comes to finding derivatives and integrals, in general, finding derivatives is much easier than integrating because we had a whole list of procedures that I give you any type of function, you could find the derivative of it. Now, we haven't gotten to certain things like e to the x or I don't know, you could even do like inverse cosine. Some of these other functions, natural log, for instance, we'll get to those in a little bit. But in general, derivatives are very easy to calculate. You can almost always calculate a derivative of a given function. But integrating, on the other hand, that is much more difficult. There's a whole lot of techniques that you can use to help you integrate, but even that's why we have things like the trapezoid method or Simpson's rule to be able to help us in approximating because we can't find the exact antiderivative. So in Calculus 2, we're going to spend a majority of time in that class using a bunch of integrals and helping us understand all these different integrating techniques. But in Calc 1, besides looking at an antiderivative, there is one trick or technique that we will use that's not just simply algebraic manipulation. So this is going to be called integration by substitution. So some integrals are going to look similar to ones that have a nice and easy antiderivative. So there's things that you should know how to find antiderivatives of at this point, right? Powers of x's you need to know how to do. You need to know how to do things with sine or cosine or using other trig types of rules. But this one here, cosine of 2x, this looks a lot like cosine x, right? You know how to find the antiderivative of cosine x, that's sine x. But what if there's a 2 there? How does that change things for us? Because remember, when we took derivatives, if we took the derivative of cosine of 2x, that's different than the cosine of x, right? Because you had 2x, you had to use the chain rule. So how do we somewhat deal with that process now with integration? Because we know they're a little bit different, but they're not the same. So we're going to call this u-substitution. U-substitution is the name of this method for this section here. We're going to replace a piece of our integral with u. So we're going to substitute in u to take the place of something in terms of x's. Then we're going to integrate with respect to the variable u. So u comes into play. We're going to integrate with respect to u. Then at the end, we're going to substitute back in terms of x. Because, for instance, this, I need to say what function in terms of x has a derivative equal to this. So I don't want u's as my final answer. So to work through this example of cosine of 2x, we're saying, well, that's very similar to cosine x, right? But we're not going to have x appear. We're going to introduce u. So what this looks like is we're going to say, let u equal 2x. So this piece right here, this 2x, if that becomes just a single variable, which we'll call u, that is great for us. So this is going to now be the integral of cosine of u. But remember, this dx over here, this corresponded to saying x is the variable that we're going to integrate. Here we have u. So I don't want a dx because I'm integrating with respect to u. So I need to figure out how do I get something with a du there. So if you think back to before this last exam, we introduced differentials. So we said we could rewrite things by taking derivatives of both sides. So you had those weird problems of du or dy equals something with x's and dx's. So we're going to do differentials. Or in other words, what you're going to do here is you're going to take the derivative of this. So if I have u is equal to 2x, I'm going to take the derivative using differentials. So this is going to be du is equal to 2 dx. So I take the derivative of 2x, I get 2. Then I write dx next to it. Here, instead of u, I write du. So I basically go through this derivative process, but introduce this du dx's. Now I'd like to substitute in not only something for 2x, which I have done here, I'd also like to substitute something in for dx, which I almost have here, but there's a factor of 2. I'm going to solve this for dx. I'm going to divide this by 2. So now dx is equal to du divided by 2, and now I can substitute that in. Du divided by 2. Now remember, one of the things that we can do with integrals is we can pull constants outside of the integral. So if I pull out this, I have a 1/2. This is going to be equal to the integral of cosine u du. Now I can simply find the antiderivative of cosine of u. We know that's going to be sine of u. The derivative of sine is cosine, so that makes sense. So the 1/2 stays in front, and I'm left with a sine of u plus c. So don't forget your plus c. You're still finding these indefinite integrals. But this doesn't make sense, right? Sine of u doesn't make sense to say that is the antiderivative of cosine of 2x dx. I need to introduce x's again. So we substitute back in. So I have 1/2 sine of 2x plus c. And so this is my solution. And you can check this, right? You can verify this process always by taking the derivative of this and seeing, do you get cosine of 2x? Remember, if we take the derivative of 1/2 sine of 2x, the 1/2 stays in front. The derivative of sine is cosine. You rewrite the inside, so you'll have 1/2 cosine of 2x, and then the chain rule says you multiply that by 2. So if you have 1/2 times 2, that becomes 1. Cosine of 2x, that's that. The derivative of a constant is 0. So indeed, this is our solution. So let's take a look at a few other examples now, going a little bit quicker through u-substitution. So when we look at these, we want to say, okay, can I pick something that would work? So here, I would pick u. So I'm going to say, let u equal 2x minus 1. Then I immediately take the derivative using differentials. So du is equal to 2 dx. I solve this for dx to allow me to substitute this in. So this is now the integral of the square root of u times du divided by 2. I can pull out the 2 out front because that's a 1/2. And I'm going to rewrite this as u to the 1/2 du. Then I add 1 to the power of u and divide by that power. So this gives me 1/2, and I have u to the 3/2 divided by 3/2 plus a constant. And now I multiply this, so I have 1/2 times 2/3 u to the 3/2 plus c, or in other words, this is going to be 1/3 u to the 3/2 plus c. But we said, remember, that we don't want u, this should be 1/3. We don't want u, we want x's, so I substitute back in at the very last step. So this is going to be 1/3 times 2x minus 1 to the 3/2 plus c. Now, a few questions you might be having when I work through this is, wait a minute, okay, you distributed the 1/2, but you didn't really distribute the 1/2. Shouldn't this be 1/2 times c? But c is just an arbitrary constant. All it means is that it's any constant that we want it to be. So if you take 1/2 and you multiply it by a constant, you just get another constant. So nothing's going to be different. I just allow the constants to just simply become c and just stay as c. So this is my final answer that you could, again, check your work if you would like to. So now if we go on to this next one, if you're thinking, okay, u-substitution, because we're doing u-substitution, well, you're like, okay, well, maybe I would pick this, right? I could pick that. So what if I said, let u equal x squared plus 1? Then when I do my differentials, I take the derivative of x squared plus 1, I get 2x, and then I throw in a dx there. So I would like to substitute in things over here, so that way there's just u's. Right, that was our goal, is I had x's here, I want only u's. Here, I have something for this inside. The inside is going to be u, and that's going to now be squared. Dx, well, I could somewhat solve for dx, right? I could divide over 2x, and I have du over 2x. But that's a problem, because then I still have an x there, and I don't have any way to get rid of that x. So this is actually not going to use u-substitution. If you ever get to the point of u-substitution and this derivative doesn't really have something to plug in here, try a different technique. If nothing else works, then see if you can go back and if there's a way to manipulate it. But in general, if this part of the differential doesn't also appear in there, then with a variable there, then we need to create something new. So the technique for this is just use algebra. You can always expand expressions and multiply them and divide them and so on and so forth. So this, I'm just going to multiply this out. X squared plus 1, when I square that, that becomes x to the fourth plus 2x squared plus 1 dx. Now this simply requires me to use my regular integrating skills. Add 1 to the power, divide by the power. So I have x to the fifth divided by 5 plus 2x cubed divided by 3 plus x plus c. And that's my answer. No u-substitution necessary. Now here, you could do the same exact thing. You could expand this out, multiply everything, just like how we did over here, and then distribute the x everywhere. That's fine. But this could also be done with u-substitution. So we're going to revisit this attempt that we had. And so if we say let u equal x squared plus 1, then du is equal to 2x dx. Now, we never ever want to try to move one of these variables over here. Constants are okay, right? So what we did up here by moving the constant over, that's great. We can do the same thing here. I'm going to divide over 2. Now, what I have x times dx appears here. So that will be substituted for du over 2. And I have x squared plus 1 here, so I have enough things to substitute in that this becomes the integral. I have this 1/2 that I'll pull out front. I just already know that. I've seen it in 2 examples now. I can pull out constants out here. I pull that out. My x dx is the du over 2. I have the 1/2 there. I have my du. And then this, u was x squared plus 1. This becomes a u squared. Now I simply integrate this with respect to u by adding 1 to the power, dividing by that power. I have 1/2 u cubed over 3 plus a constant. So now I can distribute this 1/2 inside. So this gives me u cubed divided by 6 plus a constant. But again, remember, the last step we want to do is substitute back in terms of x. So this gives me x was x squared plus 1. I have x squared plus 1 raised to the 3rd power divided by 6 plus a constant. And you could, again, check this if you wanted to. Take the derivative, verify this by using the chain rule, and you would indeed get that expression. So, again, this allows us to see some u-substitution and when u-substitution does not work, because it's not always going to be the solution and always the technique. We have to figure out when do we do algebraic manipulation, like squaring things and multiplying them out, versus when are we allowed to use u-substitution.